Hi everyone, and welcome to today's session, which is going to be on calculating the empirical formula. But before we can do that, we need to know exactly what we mean by the term empirical formula. So in any molecular formula of a compound, it tells you exactly how many of each type of atom are present in any one molecule. So for example, let's look at this molecule here, which is ethane. Now ethane has the molecular formula C2H6, and we can check that. There are 2 carbons, so there they are, and there are 6 hydrogens. So that's its molecular formula because there are 2 carbons and there are 6 hydrogens. So we write that as C subscript 2 H subscript 6. So that's its molecular formula. However, if we wanted to know its empirical formula, well, that's a very different thing. And that's basically the simplest whole number ratio. And obviously, you should be familiar with ratio because you do it in maths. And what this is saying is that for every 2 carbons, there are 6 hydrogens, but I can write that in a simpler version known as the empirical formula, and therefore 2 goes into 2 once and 2 goes into 6 3 times. So the simplest whole number ratio would actually be C1H3, but we don't write the 1, we just leave it as CH3. And sometimes the empirical and the molecular formula of a compound are the same. For example, like water, H2O, well, we can't get any simpler than that. So actually water's molecular formula is H2O and its empirical formula is H2O. So what we're now going to do is have a look at an example using some data. So what we're going to do is find the empirical formula using some masses of data that we know of 2 elements that react together. So we've got this question that we know that 21 grams of a particular hydrocarbon is made up of 18 grams of carbon and 3 grams of hydrogen. So you would write carbon and hydrogen at the top and put your values in, 18 and 3. What we now need to do is divide those numbers by the relative atomic mass of each element. Now you find this information from the periodic table. We've been doing this over the last couple of weeks, and be sure that you actually use the relative atomic mass, not the atomic number. So the relative atomic mass is the larger of the 2 numbers, and in this case carbon is 12 and hydrogen is 1. And when you divide those 2 numbers, you will notice you get 1.5 and 3. And what you should also notice is that actually this is in the ratio of 1 to 2. And one way around this is if you actually divide your smallest number by itself, you need to do the same with the other number. So in this case, 1.5 divided by 1.5 would give you 1, and 3 divided by 1.5 would give you 2. So we know now that the simplest ratio of these 2 elements are in fact a 1 to 2 ratio. So this actually means that there are 2 hydrogens for every 1 carbon. And therefore the empirical formula must be C1H2, and we would therefore just write that as CH2. So using the technique I've just shown you, I'd like you to have a go at this question. 100 grams of an oxide of carbon was found to contain 27.3 grams of carbon and 72.7 grams of oxygen. Calculate the empirical formula of the compound. So again, put your carbon, your oxygen, put the masses underneath, divide those masses by the relative atomic mass of each element and see if you can work out the empirical formula. Pause the video now and have a go. So hopefully you've done that now, and hopefully you've worked out that the formula was in fact carbon dioxide, CO2. As you can see, you put the mass there, you divide it by the relative atomic mass, and you end up with 2.28. Over here, we had 72.7 grams of oxygen. The relative atomic mass of oxygen is 16. Again, those values are there in the periodic table, and you will have one of those in the exam, and you get the answer of 4.54. Well, to work out the simplest number, whole number ratio, you just divide by the smallest number, and that gives you a ratio of 1 to 2. For every 1 carbon, there are 2 oxygens, giving us the empirical formula CO2, carbon dioxide. So again, let's have a look at another question, this one number 2. A compound was made by reacting nitrogen with oxygen and was found to contain 15.2 grams of nitrogen and 34.8 grams of oxygen. I'd like you to calculate the empirical formula of the compound. Pause the video and have a go. Okay, let's go through the solution. As before, you should have laid it out with nitrogen and oxygen, and hopefully you worked out that the empirical formula is NO2. Again, you label nitrogen and oxygen, you put the mass of each element underneath each label, you then divide the mass by its relative atomic mass, and again you get those from the periodic table. Nitrogen is 14, oxygen is 16, and here we get 1.09, 2.18. You should see that if you divide that by 1.09 you get 1. So let's divide 2.18 by 1.09 and you would get 2. So therefore they're in a 1 to 2 ratio. For every 1 nitrogen there are 2 oxygens. So the empirical formula would be NO2. Okay, so let's move on to question number 3. A little bit more detail in this one because you've now got 3 elements that you have to contend with. 50 grams of a compound contains 22.4 grams of potassium, 9.2 grams of sulfur, and 18.4 grams of oxygen. Calculate its empirical formula. Again, if you divide through by the smallest number, you should end up with a whole number ratio. Pause the video and give this one a go. So let's go through the solution to this. You should have worked out that the empirical formula should be K2SO4, which is potassium sulfate. Again, I put the masses underneath the elements. I divided through by the relative atomic mass from the periodic table, and this gave me 0.57, 0.29, 1.15. If I divide everything through by 0.29, I would get 1, 2 and 4. So there are 2 potassiums for every 1 sulfur for every 4 oxygens. Empirical formula K2SO4. Moving on to question 4. This time 100 grams of a compound was found to contain 53.3 grams of carbon, 15.4 grams of hydrogen and 31.3 grams of nitrogen. Calculate the empirical formula of the compound. Same technique, guys. Pause the video and give it a go. Okay, let's look at the solution. You should have worked out that the empirical formula was C2H7N. Again, you write the elements out, you put the masses in, you divide by the relative atomic mass found from the periodic table, and you should have got 2.2, 15.4 and 4.4, and when you divide through by the smallest number you end up with 1, 2 and 7. So that's C2H7N. Okay, 2 more questions to go. Question 5, you'll notice slightly different. This time an unknown compound was found to be 82.4% nitrogen and 17.6% hydrogen by mass. You do exactly the same, guys. Instead of putting the masses, you put the percentage and divide through by the relative atomic mass. So it's the same process, and it works exactly the same whether or not you're given the masses in grams or whether or not you're given the composition as a percentage. So same method, pause the video, give it a go. So once again, let's have a look at the solution, and you should have worked out that this was NH3, ammonia. Again, it's just a question of dividing the percentage this time by the relative atomic mass, and nitrogen is 14, and the same over here, 17.6 divided by 1. Again, divide 15.9 by itself to find the smallest whole number ratio, giving you 1. And obviously 15.9 goes into 17.6 3 times. So the empirical formula is NH3. So this is our last question for this part of the session. A compound is composed of 52% zinc, 10% carbon and 38% oxygen by mass. Calculate the empirical formula, same method, give it a go and pause the video. Okay, so the solution to number 6. You should have worked out that the empirical formula was zinc carbonate, ZnCO3. And I've put again the solution up here for you. Again, you just put the percentage and divide by the relative atomic mass of the elements. Divide through by the smallest number. So 0.8 divided by 0.8 is 1. 0.8 divided by 0.8 is 1. And 2.4 divided by 0.8 is 3. So we end up with ZnCO3, and that's the formula, or should I say the empirical formula of that compound. So before I get you to do empirical formula worksheet 1, I just wanted to go through how to tackle these sorts of questions on question 3. So what you have to do is convert these to the simplest whole number ratio. So let's take an example such as this one here, 1.48 to 1. Well, you might think, well, how on earth can I convert this to a whole number ratio? Well, actually, first thing we need to do is tackle this number here, and we need to convert that to a whole number. And actually, one way we can do that is by multiplying it by 100, so that now becomes 148 to 1. But if I multiply this by 100, I must do the same to keep the ratio the same. So I've got to times that by 100. And so therefore, you've now got this 148 to 100. What you can now start to do is maybe simplify this ratio. Well, if I divide that by 2 and I divide that by 2, I get 74 to 50. Well, if I then divide it by 2 again, I'm going to end up with 25, and this is going to end up as 37. So actually I can't simplify this anymore. So my simplest whole number ratio is 37 to 25. So that's how you would do a particularly nasty one like this. And again, you would just do the same with all the other numbers, making them 100 times bigger so that you can get a nice whole number, and then start to simplify it by trying to find a common factor. I hope that helps. What I'd now like you guys to do is please have a go at worksheet 1. Thank you. So here is worksheet 1, empirical formula 1. I'd like you to have a go at this worksheet, please. You'll notice here's question 3, and I've just shown you how to do these sorts of problems. So again, make sure that you watch that video again if you can't do it, and it will show you how to convert more complicated decimalized ratios into whole number ratios. And then the rest is fairly straightforward. When you come to the end of this worksheet, you'll notice that there's a little review box at the end, and here it is. And I'd like you to red, amber, green this. So obviously, if this particular area is a strength, you would colour this as green. If it was red, in other words, you really struggled with this, then shade it in red and set it as an area to develop. You could then go back, relook at the video, and maybe have another go at those questions. Once you've completed this worksheet, please download the answer scheme, go through the answers and mark your worksheet and give yourself a tick, and you'll soon see where those areas that you went wrong and those areas that you might need to develop, as well as those areas of strength. Hope you found this useful. Pause the video, have a go at worksheet 1, download the answers and mark your work. Okay, just as a final from me, there is a second worksheet you guys can have a go at. It's Empirical Formula 2. These towards the end get a bit more trickier actually and require a little bit more thought, particularly questions 3, 4 and 5. Again, when you finish this worksheet, you can have a look at the little self-assessment. You could red, amber, green it, see what your strengths are, see what areas you need to develop, and then maybe re-watch the videos should you need to just tighten up 1 or 2 areas. Again, from Teams, you can download the mark scheme, mark your work, identify those areas that you need to develop, and I'll look forward to seeing you next time. Take care. And for those of you who are not at UTC Swindon, I'm just going to scroll through the answers so you can self-assess your work. So here are the answers for Empirical Formula number 1. And here are the answers for Empirical Formula 2.